The objective of this lesson is to understand how to assign oxidation numbers to any chemical substance. So to turn it into an I can statement, at the end of this lesson you'll be able to say, I can assign oxidation numbers to any chemical substance with these rules. So here are the rules for assigning oxidation numbers, and I'll try to give you some concrete examples as we go through them. The first rule is that elements in their elemental form have an oxidation number of 0. So elemental oxygen, which is diatomic, has an oxidation state of 0. Lithium in the metallic state has an oxidation state of 0. Iron in the metallic state has an oxidation state of 0, and so on. Second rule, the oxidation number of a monatomic ion is the same as its charge. So a sodium cation with a charge of +1 has an oxidation state of +1. Calcium in the state as an ion would have a +2 oxidation state, and so on. The ferric ion would be an oxidation state of +3. The ferrous ion would have an oxidation state of +2. Third rule, nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. Typically, when a nonmetal is coupled to another nonmetal that is more electronegative than itself, then it will have a positive oxidation state. An example, for example, is the perchlorate series. Perchlorate, chlorate, chlorite, and hypochlorite. You'll see the chlorine atom having a decreasing oxidation state. In perchlorate, chlorine has a +7 oxidation state. In hypochlorite, I think it's +1. We'll see a few examples of that. Oxygen is -2, except in peroxide, where it is -1. In superoxide, the oxygen will have actually a -1/2 oxidation state, because you have two oxygen atoms sharing a -1 charge. So you don't have to necessarily have integer values. Sometimes you'll have partial oxidation states. It happens. Hydrogen is usually +1 when it is bonded to a nonmetal. For example, in hydrochloric acid, hydrogen is +1, whereas chloride is -1. When hydrogen is bonded to a metal, on the other hand, it'll have a -1 oxidation state. Hydride, like hydride. With fluorine, the oxidation state is always -1. Fluorine is the most electronegative element, so it does not share electrons with anything. Or at least, well, it forms covalent bonds, but when in the covalent bond, the electrons are closer to the fluorine atom, and typically fluorine, because it is the most electronegative element, will pull the electrons away from anything else. Other halogens are normally -1, except in oxyanions, where they have positive oxidation numbers. For example, like I mentioned in perchlorate. Finally, in a neutral compound, the sum of oxidation numbers is 0. So let's say, for example, chlorine dioxide, which has the formula ClO2. The overall oxidation of the number of the whole compound is 0. It adds up to 0. The oxygens are -2, and there's 2 oxygens in chlorine dioxide, as you can see here, so that would give a -4 oxidation state. Because the molecule is overall 0, then that means the chlorine has to be +4. Here are some examples. Oh, one last rule. In the polyatomic ion, the sum of the oxidation numbers is the same as the charge on the ion. And we can see an example of that right here in 1A. Nitric acid. Hydrogen is +1 because it's coupled to a nonmetal, which is more electronegative than it. Then if you look at the nitrate anion, nitrate is -1 overall. Each oxygen atom has a -2 charge, so it totals -6. Why is the nitrate anion -1? Well, that's because the nitrogen has to be +5 to compensate. With copper chloride, cupric chloride, copper is +2. The chlorides are usually -1 because they're halogens, so there's 2 of them. It makes perfect sense. So the chlorine is -1, each one is -1 for a total of -2. Magnesium sulfate, group 2 metals are always +2. Sulfate is -2, it's a polyatomic ion. 4 oxygen atoms at -2 each, so a total of -8. But the overall charge on the sulfate is -2. That must mean that the sulfur atom is +6. potassium chlorate. Group 1 metal, +1. And the chlorate anion is -1 overall. It's comprised of 3 oxygen atoms, each with a -2 charge, so the total is -6. But because the perchlorate anion is -1 overall, it must mean the chlorine atom has a +5 oxidation state. In ammonium perchlorate, we have 2 polyatomic ions making up the compound. Nitrogen has to be -3 to compensate for the fact that each hydrogen is +1. Remember, nitrogen is more electronegative than hydrogen. So the hydrogen will take on the positive charge for them. Overall, the cation is +1. So that's achieved by having 4 pluses and 3 minuses. Nitrogen has to be 3 minus in this cation. The perchlorate anion, when you can compare it to the chlorate one, you'll see that there are 4 oxygens, each at -2, so a total of -8. The perchlorate anion is -1 overall, therefore it must mean that the chlorine is +7. So you see that in perchlorate, chlorine has a higher oxidation state than it does in chlorate. Chlorine dioxide we've already mentioned. And finally, in sodium hypochlorite, you have a group 1 metal with a +1 oxidation state. The hypochlorite anion is -1 overall. There is 1 oxygen atom at -2, and to get that -1 charge, overall you have to have a +1 oxidation state on the chlorine atom.